This last talk of this conference. So we have Carsten Petersen and from Roskilde, and he'll be telling us about taming elephant families.
So I guess taming elephants in India is the right place. But let me just start by telling you where my usual habitat in India is. And I'm very thankful to all of you Indian mathematicians which are now becoming part of my mathematical family. So I have other reasons to come to India than to stay in my habitat. What are elephants about? So here's an elephant upside down. It's a true limiting elephant. It's a picture that was shown to me by Sørensen first time in the early 90s. So when I started my master and PhD program, Mitsu was starting to prove and eventually proved his theorem about the house of dimension of the boundary of the Mandelbrot set, which relies on parabolic implosion. If you take the parabolic implosion to the limit, you get a limiting family of maps which have a parameter space which in certain cases exhibit elephants. So maybe the elephants are more clear on this picture. And I want to, taming the elephant, what do you see in this picture here? So, I mean, it's obvious, it looks like a piece of the Mandelbrot set. Like you have a hyperbolic component, you have satellite hyperbolic components of it, so it should be like a Mandelbrot set. Or at least, I don't know, it's like the microphone is, can you hear me when I'm talking? Okay, at least this should be like a limb sitting here and maybe other limbs sitting in other places. The problem is just that in this parameter space or the underlying maps, even though they exhibit a structure that looks familiar to us, like polynomial-like, they can't be polynomial-like because there's no fundamental domain, no fundamental annulus when you try to make a polynomial-like map. So let me motivate a little bit where this picture comes from for those of you who are not experts in the field. We have seen definitions of the Mandelbrot set, so I decided not to give you a definition of the Mandelbrot set, but just give you a picture. So the Mandelbrot set is our chart of the dynamics of quadratic polynomials. So for this trained eye, we can just look at it, point to a place, and then we have a good idea of what is the underlying dynamics. We have seen or maybe been told that inside the cardioid shape here, we have a polynomial with an attracting fixed point. And this component can be naturally parametrized by the multiplier of that fixed point. So if you make the argument of the multiplier go to to 1/2, so we're always counting in rounds of 1, you go into the 1/2 limb. If you make the multiplier go to the third root of unity, you go up to the 1/3 limb. You have similarly a 2/3 limb. Then you have a 1/4. Then 3/4 here. 2/4, which is 1/2, is already taken up. And then you have like 1/5, 2/5, etc. Now, what is the dynamic in a limb? So I told you already what's in the dynamic in here. So what is the dynamics in a limb? Well, if you go to go immediately to the first hyperbolic component off. So what I'm doing here is I'm going to the fourth one. I'm going to the center just to have a good picture. Then you see that you have a fixed point. You have a component of the filled Julia set containing the critical point. And the critical point is actually 4 periodic. So the critical point 0 goes to the critical value C which goes to some intermediate value, some other intermediate value, and then returns to 0. So, and it does this in a rotation by 1/4 fashion. So that's why we call it the 1/4 limb. So it's tempting to take the 4th iterate and restrict the dynamics to the 4th iterate. And this is what I've tried to indicate here. So I outlined something which is a polynomial-like map. So in general, a polynomial-like map, as it was told to us, is a proper map F from a disk U, relatively compact, contained in the range U prime of some degree. So in this case, the first return map, you can, if I can have the light off, please. I have made a domain outer U prime, and its pre-image U, and we have a quadratic-like restriction. So I'm using the word here quadratic-like restriction rather than polynomial-like restriction because Misha, in order to create a proper theory for polynomial-like maps, have shown us that we should really work in the marked polynomial case where we're not just working with Riemann surfaces, as was originally proposed by Doherty and Hubbard. We should work with open subsets of C. We should work with maps where we put the critical point at 0. And so the first terms are C plus C squared plus etc. And what Misha has shown to us is that under very general conditions, if you have a holomorphic family of quadratic-like maps, then that family actually contains a copy of the Mandelbrot set. The point that we are addressing here is that somehow this theory does not apply because, so you see already here, it seems that the outer and the inner annulus is very pinched, like this. And in the limit where you get pinchings, then the theory doesn't work. You have to come up with other things. Luna has, in her PhD thesis, come up with a case where you can sort of handle if it's a parabolic point. But it turns out that the limiting situations that we get out of these is very pinched, so pinched that you have to do something else. So here you may have the idea that it's getting pinched. I don't even know how big the Q is, but if you look at this copy here, the one containing 0, then you have all its siblings in the orbit, and you don't have a lot of room to create a polynomial-like map. And in fact, when Q goes to infinity, you lose completely the space. So let me just, well, so here, how can we understand then this structure of the limbs when Q tend to infinity? And the answer that's given to us is it should be the limiting family, the elephant family. But we have understandings of different parts of that family, but a priori there was no understanding of like the principal limbs. So how can you single them out? What is the dynamics in there? So this is the goal of this project, was to understand this. So let me just make a couple of zooms into the cusp of the Mandelbrot set to see how these elephants arise. So eventually you see an upside down elephant here. Maybe a better picture. So as I said, the problem is that the limiting maps are extremely, well, they are really pinched. So if you change coordinates for your nearby maps, so you send the two fixed points to 0 and infinity, take a logarithm, then you get a picture like this. And in fact, I'm pretending that this is the limiting map, even though it's actually just a quadratic polynomial where you've done something similar to that, and then for a very large Q. but what you have are transcendental maps eventually in the limit, which actually are coverings, well, branch coverings, and which commutes with translation by 1. So when you do this blow up, you should normalize so that the dynamics gets approximates translation by 1. And as I said, there is no way to hope that such maps can be quadratic like in the usual sense. So here are more pictures. You can see here something that should be a rabbit. This one is probably a center. So in order not to just work with the limiting elephants at 1/4, we decided to have a more general theory and consider a class of maps defined by 5 axioms or properties. These properties are satisfied by horn maps when you have a quadratic basin of a nearby parabolic, but or of a parabolic, but somehow there's no statement of parabolic here. So Dirk was saying that he has to carry the banner for the transcendental maps, but here is really a class of highly transcendental maps. So they are maps which are defined on, you should think of an upper half plane. So a domain U, which is bounded from below by translation by 1 invariant Jordan curve. You have a map which goes everywhere to C, acting as a branch covering with up to translation by 1, only 1 critical value. Let's put it here, but it could be anywhere. So outside the critical values, I mean, you have evenly covered neighborhoods of points. I don't know if I said that. It should commute with translation by 1. And if you go north, so if you go towards imaginary part to infinity, it should be asymptotic to a translation. And finally, there should be a dense set of, we call them roots. So what is a root? It's a touching point of a topological Horner disk, which maps to either an upper half plane or a lower half plane, univalently. So why this class of maps? So if you take a symbolic drawing of the Mandelbrot set, then okay, in here you have elephants. If you go down here, you have smoking elephants. And I don't think elephants near the root of other limbs or limbs of limbs have names, but there are elephants in quotation mark everywhere. And by working in this class, we are sort of doing something for all the cases, so which is good. So here is an example. This is from the quadratic family, so it's similar to Z squared. I think Mitsu was using this as a model for modeling his first space of invariant class for parabolic renormalization. So red is mapped to an upper half plane. Green is mapped to a lower half plane. Critical points here. So they, of course, once you have one critical point, translation by that becomes a critical point. So there is actually a component of the preimage of the upper half plane above the critical values, which is a true upper half plane, well, with a Jordan boundary containing critical points on the boundary. And for what we're going to do today, we're going to assume that the order of these critical points is always 2, or is 2 for one and hence for all of them. But we don't really make assumptions about deeper critical points. Yes?
So why are the critical points at the boundary in green?
So what I did is I took the line through the critical values.
Ah, okay. And what was your notion of root point?
So the roots is like a touching point of a colored region. So it's a domain which maps univalently to either an upper half plane or a lower half plane that will have a touching point necessarily on the boundary, because there can be no inner points that maps to infinity. So root points are points where you have, it's like an exponential tract except that the map is univalent, that this point is set to infinity. Okay? So I said most of these properties. What you should notice here is just that we have this notion of criticality for the order of the top critical points. Of course, when you have maps that commute with translation by one, it's tempting to do the quotient. Let's define the projection to C star by e to the I2 pi z, and then do a semi-conjugacy of our map in class H to map on C star. Then, because you have this property that H of Z is asymptotic to Z plus some constant at plus I infinity, the map below will extend to 0 with as a fixed point with a multiplier which is e 2 pi I capital A. So the quotient maps belongs to a class of finite type maps. So somebody chose to define, we call them Adam maps or Adam Epstein maps. So what are they? They are similar to above, but they're just the projection of that. So they have a domain which is Jordan disk containing 0. They have a fixed point at 0 with some non-zero multiplier. The restriction to the disk omega minus 0 is a branch covering of C star. 0 and infinity are asymptotic values, and there is a dense set of points in the boundary, which again we call them roots, where you have a Horo disk which maps as universal covering of either a neighborhood of 0 or a neighborhood of infinity. So the natural deformation space for such maps is to, for those in the Horn class, is just to add a translation, and that becomes that of multiplication in the Adams class. And you can also conjugate by translations, and so there's a natural space or a normalization, which is that the translation at plus I infinity is 0, so it's tangent to the identity at plus I infinity, and the critical values are put at the integers. Then similarly, downstairs you have maps which have a parabolic fixed point at the origin and critical value 1, a single critical value 1. And so take a map up here, do the semi-conjugacy, you get a map in an Adam map. So I said the natural deformation space for Horn maps is to post-compose them with a translation, because you need something that commutes with translation by 1. The whole range is all of C, so there's not so much choice. So if you pick a map H in H0, then we could define H lambda to be H translated by lambda. And then here I've tried to illustrate something we call race. And for that, I need some more blackboard space, or I reserved some space here. So to understand that, so here's my boundary. I have an H in H0. So I have a little h in A0, which has a parabolic fixed point. Having a parabolic fixed point, you very quickly see that, in fact, there must be a whole basin of a parabolic fixed point. Oh, I shouldn't draw it like that. I should draw it more like this. And the critical value in the basin, there's only one. And then the critical point is the top critical point. So it's a quadratic basin. So I have a quadratic basin for H in A0. And when I have a quadratic basin, let's take the Fatou coordinate and wrap it up on a cylinder. So to put the critical value, say, at 1, then you can lift this core curve on the cylinder to a curve which is invariant by the dynamics. And it will eventually reach out to the critical value. Then pre-image goes to the critical point, and next pre-image will have to go to a pre-image of 0. But 0 is an omitted value, so the other end has to go to the boundary. So that gives me a curve which, well, it folds on itself, but it's forward invariant, and it connects the boundary to the origin. Now, if I lift that curve up back here, I get curves going from plus I infinity to the real line. And I have a lot of them because I translate by one, I have a new one, etc. Let's call this landing point here beta 0. We could call this one beta 1, and here beta minus 1. And let's look at the pre-image of the lower half plane. Well, actually, maybe you should look at something else. Let's look at the pre-image of the domain going here like that. So did you see? It's a simply connected domain, which does not contain any critical values. So the pre-image is again simply connected and maps univalently onto this domain. But we know that along the boundary, the dynamics is going in here. So in fact, it has to have a pre-image with something like that. And then,
you don't have a critical value there?
well, the critical value is on the ray.
Oh, okay.
So that's a good point. So that was essentially why I wanted this. This was to take care that I don't have my critical values in my domain. And so in fact, this must be part of a pre-image of the lower half plane. So there's an arc here which maps one-to-one onto a fundamental domain, and then I have another one which maps to the next, etc. Like that. And moreover, this was the beta fixed point, or the pre-image of the parabolic point. So we know that if you have a parabolic domain, so if you take the pre-image of this arc, it's going to give you an arc through the critical point, connecting 2 points on the boundary and going through pre-images of the critical point. So we have a natural model for this, which is the Blaschke product, which appeared in Luna's talk. So there it was called is it B2 or B3? It should be B2. Yes. And so these, in some sense, these are the points of argument 1/4. So you have here points which should correspond to argument 1/4. The are pre-images of this, so that means that if I look at the boundary or the basin, my parabolic basin, it must come and touch this circle here. And similarly with the other one. So this one, of course, has its sibling, which is translation by 1, which does similar things, etc. And now, again, because we are away from the critical values, this one will have a pre-image inside. And it will have, again, a pre-image inside, univalent, etc., going up north. And by translation, I have the same here. And there, of course, I have lots of other pre-images of the lower half plane. They somehow tessellate what we could call the escaping set, the set of points which escapes in finite time. Well, either you escape in finite time or you don't escape. We have called them lagoas from Misha's sort of favorite place in Rio, I guess. And in some sense, those familiar with like old literature have heard about bubble rays. So they are, in a sense, like bubble rays. To come up with something sort of to better be able to define maps, what we will do is we will take, say, a hyperbolic geodesic going to minus infinity in the complement, and it's translate. Now, this was, this arc goes 1-to-1 here, so there's a pre-image inside, which has a further pre-image, which has a further pre-image. And in this way, you actually construct an arc in the complement of the parabolic basins, or virtual parabolic basins, connecting boundary to infinity, but naturally chopped up in dynamical pieces. So one piece is mapped to the next. If you take this arc here, which is again like a fundamental domain, then you will find that another is like a copy of this one. So let me just complete up here. So I will also have a pre-image of this arc going like this. And I could even take the complete pre-image and it'll have to converge to the beta fixed point, or the beta, this beta 0, the pre-image. Similarly, I have a disk here, a pre-image of this disk, and I have an arc here converging. So now let's start doing some naming. Call this piece here 0. This arc here 1. This arc we could call 0, 0. This one 1, 1. So doing a labeling which sort of is consistent with dynamics. That, okay, 0 and 1, they're out of range, they're out of bounds, but 0 has two pre-images, one inside here, which we could call the lagoa 0, and then the pre-image of the 0 ray inside the 0 lagoa would be 0, 0. The pre-image of the 0 ray inside the 1 lagoa would be 1, 0. The pre-image up here would be 0, 0, 0, and then 4 zeros, etc. 1, 1, 1, 1, 1, etc. And so it would be natural to label this ray here by the symbol 0 repeated. And this ray here by the label 1 repeated. The ray you obtain here then naturally is first 0 and then 1, 1, 1, 1, 1. So this one is 0, 1 repeated. And the ray here is 1, 0 repeated. Yes?
Question. So, taking a big step back, did you say to get this whole discussion started, you assumed that the multiplier at the origin
Was 1 just to start.
Okay.
Okay, so I can do this in first in that plane. Okay. And it turns out that if I want to take all those lagoas and ray pieces, which stays in here forever, then they are naturally labeled by dyadic labels as I started to. So the rays I obtain by only staying in here are naturally in correspondence with the symbol 0, 1 to the power n, which is very familiar to us for the Mandelbrot set, because there, okay, we have rays of argument theta, but theta should really be understood in terms of its symbolic sequence here. So, for instance, we know that 0, 1 is 1/2, and it's also the same as 1, 0, etc. So we really read it as 0 dot and 0 dot, etc. So all these things. So also you can simply extend the picture and say, okay, if I have my theta and q theta, q, what is it? 2 to the q theta is congruent to theta mod 1. Then I have a q cycle. I can express this unique, so theta then uniquely in dyadic expression, and then there will be a unique ray also for that. So it very much resembles the picture we have. It's just that what is the map? And so maybe I should say also that we have a natural holomorphic motion of lagoas. So like starting from the level 0 lagoas, so there are lots of them down here I didn't draw, they naturally move holomorphically with the parameter, the translation, over the whole upper half plane. And this holomorphic motion, in fact, extends the identity holomorphic motion in the lower half plane. In particular, the root is fixed. So if I do a labeling for 1, say for H0, then I can use that labeling for every one, and it will be consistent with my holomorphic motion.
What is the parameter for the holomorphic?
It's the critical value. So somewhere. So we start from H, which has critical value, the integers. And then we have H lambda. So we add composed with translation by lambda. And this is our H lambda. So the critical value set. So the critical value set, or the critical value, principal critical value, you could say, is also the parameter.
When you move the parameter, you don't have a bifurcation of these images, the lagoas?
Not for the level 0, because that would require that the critical value was outside. But if the critical value did not escape, then the level 0 lagoa, or level 1 lagoas does move holomorphically. Now, if my critical value doesn't escape after 2 iterations, well, no, even after 1 iteration, then I can do the next level. They move holomorphically, and I can continue upwards. In particular, as long as my critical value doesn't escape onto level n, then all my level n lagoas are well defined. And how will lagoa stop moving holomorphically? It will stop moving holomorphically if somewhere forward along the path, you have a critical point. If the critical value is in there, it's okay, but critical point being in there, then that's a hindrance for holomorphic motion. So I claim that you can move holomorphically as if you are close to zero, then you move holomorphically very far up. But in fact, how can like the 0 and the 1 ray stop moving holomorphically? Only by the critical value being on one of them. Well, if I have a critical one, then the translation by 1 here is also. So the only way I can break having a 0 ray going from the boundary all the way to plus I infinity is by my critical value moving into this, and I mean that ray will move holomorphically also. So I will have a domain where the rays move holomorphically. So on the other, so I have here one example. I drew in blue the curve coming from the parabolic, and white the 0 ray of argument 0, white the 0 ray of argument 1, and then the two 1/2 rays, the R01 and R10.
Where are the betas in your picture? The beta not?
So beta can, in the family, beta can be anywhere in between, between two.
No, but
Sorry, the root here can be anywhere in between beta and its translate, and here actually the beta and the root coincide.
Oh, you chose them.
Well, I chose, it's because I made a parabolic picture, and there it just happens to be the case. But in our, with our conditions, there's nowhere saying that beta 0 should coincide with the root of level 1 lagoa. Okay.
Where is that in your parameters? So the left picture?
So let me, before I answer that question, okay. So because you have this holomorphic motion, you can actually transfer your labeling of dynamical lagoas to parameter space. So you have also parameter lagoas corresponding to escaping parameters. So here are level 1 parameter lagoas corresponding to the 0 and 1 lagoa. 0 and 1. And I have also a 0, 0, a 0, 0, 0, etc. I have a 1, 1, 1, 1, 1, 1, etc. And because these rays move holomorphically, and in the parabolic case, they actually land at the parabolic fixed point, then it's sort of almost more standard nowadays that then you can, by the shooting argument, show that the corresponding parameter ray, 0 ray and 1 ray, land at the parabolic parameter 0 in this case. So they chop off a subset, a whole elephant in parameter space. Yes?
How do we know these parameter rays are mixed? How do we know the dynamical rays actually work?
So what you have to see, well, you have to, I'm sort of hiding a lot here, that on every parameter lagoa here, so it's characterized by that the critical value is in the corresponding dynamical lagoa. And so if I, for level 1 lagoa, apply the map H lambda to the critical value, it will be in the lower half plane. And so what you have to show is that that map from your parameter lagoa to the lower half plane is a biholomorphic map. And it is. And it's true whichever, so you take any parameter lagoa, then the appropriate iterate on the critical value will define a map from your parameter lagoa to the lower half plane or to the complement of the domain. Okay, did I answer the question? Can I have light? So, maybe I lost track. Can I just? So, the shooting argument will tell you that you have a 0 parameter array, 1 parameter array co-landing at 0. Now, Milner has developed, and I have another proof also, that when these two rays, well, these rays land at a parabolic point, if you go in the transverse direction, they stay landing at a repelling fixed point. So what happens when you move lambda south, so south of 0, so is that the fixed point here, which was parabolic, split off into 0, which becomes repelling. And then when you go south, what you split off is attracting. And the rays that came in here, I made them red. So they are, in this picture, they would be just one ray sitting inside some lagoa. Like this. It has to touch on two sides. Okay. Will persist landing at 0 while then suddenly, so now 0 is the landing point, and then I have an attracting fixed point with 0 as the repelling fixed point on the boundary. So if I move a little bit, I come into a hyperbolic component where I have a fixed point which is attracting. And again, by standard arguments, the multiplier of that fixed point defines a defines a holomorphic map from the hyperbolic component onto the unit disk. And let me have some light. So I want to define now a pinched quadratic map. Okay. So I'm claiming that in this parameter domain here, we can keep following the 0 and the 1 ray. So symbolically, here's the 0 ray and the 1 ray. They move holomorphically as long as I don't touch, as long as my critical value don't go to them, which happens precisely when I hit the parameter rays 0 and 1. So let's call this W0 of lambda. Now, inside I have a unique critical value, lambda. And I have a critical point, which maybe initially is above or below, or maybe it's here. Okay. And then inside I have a unique preimage, which is mapped 2 to 1 onto this. So I had, if here is the boundary, I had the 2 1/2 rays like this. So I have a domain which maps 2 to 1 onto the full strip. So it's almost like a polynomial-like map, except that it's very pinched. I mean, there's no room for a fundamental annulus, but it's 2 to 1. It's branched. So what's not to like? And my statement from before is that if I look in this family, then in here you will find a sort of central hyperbolic component corresponding to that the fixed point infinity, which was parabolic, now splits off an attracting cycle, or an attracting fixed point. Also, it's not difficult to prove that, so because it's a quadratic picture, and we have these rays, so we can label rays in the usual dyadic way. And because, for instance, if you go to the center, you have hyperbolic dynamics, you will actually find that all these rays land, and they land on this hyperbolic component, the attracting basins of the critical value, which is the critical point in that case. It moves holomorphically, so it stays landing, and you could go to one of these parabolic roots, so let the multiplier tend to a root of unity. And then what we prove is that in that case, so you have the usual picture that you come in with different rays from different sides, from a P over Q cycle. Here's the basin is like this, but they come in and meet. So I have that the P over Q cycle of rays, in that case, co-land on the fixed point, and you have the usual exchange, at least if you go directly into the domain where the Q cycle becomes attracting. So that I have the sort of standard picture that is most easily drawn in for a quadratic polynomial, but which you can do here also with the rays. I didn't sort of rehearse doing that, but I've done it lots of time. You can pick your favorite rotation number, and then you can actually draw this picture. And so you will find that your fixed point sitting somewhere, maybe here. Red. This may be the landing point of Q rays that are 1 over Q, or 1 over 3 permuted, or 1 over P over Q permuted. And so you can actually define limbs. So clicker is here.
Why do those rays go over to the vertical ones?
It's
zero ray.
yes, but it's because any ray will be indexed by something in 0, 1 to the power n. So if you write anything dyadically, either it starts with a 0 or a 1, and for instance, the what is it? 1/7 is 0, 0, 1. So it should go through 1 lagoa, and then that's 0, 0, and then it should branch off into the next lagoa. So it should branch here. So
I thought that you might be running the small circles.
but no, but you will. This is only for. This is special for 0, 1, and 1, 0. They will do this, and they did that because the image lands at plus I infinity. Before I would have like a basin, which is inside my domain, and where rays land to points in that basin. And so going to the boundary would mean that that boundary point went to infinity, or to the boundary of the domain. Okay. So I put in, maybe the slides will be somewhere, so I put in a lot of definitions, but I think I said them. So we just move forward here, the same drawing. So let me go up. This component here we call parameter W0, and it corresponds to the dynamical. Well, actually, parameter W0 is the big one. Okay? Parameter W1 will be the one that corresponds to the domain of our degree 2 restrictions. So it will be bounded by the 0, the 1, and the 2 1/2 rays. So I have, I'm going to erase this because we're not going to use that anymore. So redoing this drawing, we have W0 of lambda between the 0 ray and the 1 ray. We have inside, we have W1 of lambda, which maps 2 to 1. Similarly, in parameter space, we have the upper half plane, which corresponds to 0 being attracting, and then we have the 0 parameter array and the 1 parameter array. We have the 2 1/2. I should be red. Parameter arrays, 0 1 repeated, 1 0 repeated. So we call this domain W0. And so for any parameter lambda in here, not only does the vertical rays move holomorphically, the 0 and 1, but their pre-images also, because they're pre-images. And the fact that they transport to parameter space is just that they move holomorphically, even in the full domain. And my critical value can be anything, so it hovers over a holomorphically moving set, so it transfers into parameter space. So let's call this map the restriction here by maybe fat h or something like that. From so fat h is from W1 of lambda to W0 of lambda, and we take lambda in the disk W1 here. It's 2 to 1. It's naturally continuous on the boundary. We can extend it continuously to plus I infinity by defining that the image is plus I infinity. We can extend it to beta 0 by declaring that the image of beta 0 is plus I infinity. So it's a topological disk mapping 2 to 1 onto a topological disk. So I should say at this point, of course, you map to minus I infinity. Yes? Let me. So I defined W0. I claim that in W0, not only the 0 and 1 rays, but also the 2 1/2 rays move holomorphically. And you have this restriction from W1 of lambda to W0 of lambda, which is degree 2. And you have a restricted domain W1 in parameter space corresponding to what I drew here. Okay. So then you could define a connectedness locus for this particular family. So the set of parameters for which the critical value does not escape lambda 1. So as long as you hit lambda 1, so inside here we have lambda 1, you can iterate. So we can define a connectedness locus to be the set of values lambda such that the critical value stays in the domain of iteration for all times. And we can define similarly filled-in Julia sets as the set of points for a given parameter lambda that stays in the disk forever. Of course, it might be that eventually you hit beta 0 and then plus I infinity, but we know what to do. In the domain, you have this disk I was talking about, corresponding to a fixed point. You go to a root. Then you prove that the root rays actually converge in parameter space also. Again, this is the shooting argument. It's true for the parabolic root. And then by using the shooting argument and then for 2 coordinates, then you prove that also the corresponding rays in parameter space converge. And when you are then inside this domain here, W, you could call it P over Q, we have an intersection with the connectedness locus we could call the limb, the P over Q limb. So inside here we have limb LPQ. And should be finished very soon. So here it is, the limb. And then the main theorem is that we don't exactly necessarily have a copy of the Mandelbrot set, but all the limbs are homomorphic to the corresponding limbs in the Mandelbrot set. So we have a disk that corresponds to the body, and we have sets, connected sets, which are homomorphic to the limbs in the Mandelbrot set. In the Mandelbrot set, we know there's nothing more, because we have a Yoccoz inequality, which tells us that the diameter of a limb shrinks as the denominator go to infinity. And then from that, you can see that there are no further points. But here, because we don't have an external map, we don't have a way to control the size of limbs. So we don't know to prove that actually there's nothing more to our connectedness locus than what we know is already homomorphic to parts of the Mandelbrot set. In particular, it's not, we don't know if it's a homeomorphism because there could be other stuff and things could be larger than what they're supposed to be. Okay? Thank you.